We're going to take a look at mass spring systems, and these are super important in physics because they describe an awful lot of different systems. So in lab, we had this little gizmo where we had a spring and we hung some weights on it, and we first of all measured how does the stretch relate to the force that we apply to it, and then we pulled it out and down and it bopped up and down a ways. We called that an oscillation, and we looked at how the period depended on the mass. So we're going to talk about those two things today, okay? All right, so first of all, we asked how does the stretch depend on the force? So the stretch distance, we plotted on the y-axis. The force that we were applying to the spring, we put on the x-axis. And I think that most of you found that the stretch was directly proportional to the force that was applied. So we use this variable delta x to represent the stretch. So what we can learn from this is that the more force you apply, the farther the string stretches, and there's a direct relationship. This relationship is actually called Hooke's law, and it basically says that the force that's required to stretch a spring is directly proportional to the distance you want to stretch it. So applying twice as much force causes twice as much stretch. Mathematically, Hooke's law looks like this. The force that the spring applies is proportional to the distance it is stretched. The proportionality constant we call the spring constant, and we're going to throw a negative on there to remind us that if we pull a spring to the right, the spring itself exerts a force backwards to the left. So this negative here is just reminding us that the force that the spring applies is opposite to the direction it's stretched. So if you pull a spring to the right, it applies a force to the left. If you push a spring to the left, it applies a force to the right. So that's what the negative's about, okay? So Hooke's law is fairly important, but we're not going to do a whole lot with it. We just kind of want to conceptually touch on it. But it helps us get to the next idea, which is more important. But first, let's talk about the spring constant thing. So this K right here, we call the spring constant. So a spring constant tells us about the spring. In fact, it tells us how much force it takes to stretch it. So if the spring constant was 1 Newton per meter, so we use newtons per meter as the unit for the spring constant, a K of 1 Newton per meter means it takes 1 Newton of force to stretch it an entire meter. That is a very weak, or sometimes we say a soft spring, okay? If the spring constant was 25 newtons per meter, then it would take a force of 25 newtons to stretch it a meter. And if you only applied 1 Newton to this spring, it only stretched 1/25 of a meter, which is about 4 centimeters. So that is a stiffer spring. And if the spring constant, for example, was 500,000 newtons per meter, that would be a very strong spring. This is like the kind of springs that hold your car up. So your car is connected to your wheels by springs, and they have very large spring constants. They're very stiff springs. In this case, if it took 500,000 newtons to stretch it a meter, then if you had 50,000 newtons, you would only stretch it 0.1 meters, or about 10 centimeters. So K is just a measure of how strong the spring is, how stiff it is. Now, springs give us a very important idea, and that is what's called a linear restoring force. So a spring produces a linear restoring force. This means that the spring always applies a force that opposes motion from equilibrium. So let me try to explain what that means. So here's an illustration. I've got a mass hanging on a spring. Now, the spring and gravity together conspire to make this mass hang right here. We call this the equilibrium position. At this point right here, the force of the spring pulling up and the force of gravity pulling down. So here's the spring pulling up, here's gravity pulling down. They are exactly equal. So at this point here, the net force is 0. So we call this equilibrium. Now, if I were to displace the system from equilibrium, if I were to pull it down, the net force would be upwards. And if I were to pull it up from equilibrium, the net force would be downwards. And so that's what we mean by a restoring force. Between the spring and gravity, whichever way you move this away from equilibrium, the net force opposes that motion. So let me show you the forces on it. The blue force is the spring, the red force is gravity. If I pull this up, the spring force gets smaller, gravity remains the same, and so the net force is downwards. But if I pull it downwards, then the upwards force is bigger and the net force is upwards. So no matter which way I move it from equilibrium, the spring and gravity conspire to apply a force that opposes displacing it from equilibrium. Okay? So what happens is, if I pull it down, the net force is up. And if I let it go, it'll start moving up. Now, at some point, when it gets back to equilibrium, there's no net force on it. So you would think, well, there's no net force, it's not going to accelerate. That's true. But it has inertia. And so it keeps moving up until the net downwards force stops it. And now the force downwards pulls it down. And now the net force upwards pulls it up. And because of its inertia and the restoring force, those two things work together to cause this to oscillate, to move back and forth, back and forth. So here it is in normal time. So the spring applies what is called a linear restoring force. It's a force that attempts to restore to equilibrium. And anytime it's displaced from equilibrium, if it's above the equilibrium point, the net force is down. If it's below the equilibrium point, the net force is up. And that produces this motion and this mass bopping up and down on the spring, okay? So anytime you have a linear restoring force coupled with a mass, you get a special kind of motion, and that special kind of motion is called simple harmonic motion. Okay, and simple harmonic motion helps us explain light and sound and atomic vibrations and all kinds of things in physics, electrical signals, the radios that connect your phone to the cell towers or to your headphones. That's all examples of simple harmonic motion. So that's why it's an important idea. Okay, so you get simple harmonic motion when you have a linear restoring force coupled with a mass. And there's a simulator here. You can stop this video if you want, and you can go and play with that simulator. That's the one I was playing with here. You can hang different weights on it, and you can change the spring constant and see what happens, and you can play around with it. All right. So why do we call it harmonic motion? Well, when a mass on a spring moves up and down, if I were to plot its position versus time, I would get this graph that is what we call a harmonic function. The harmonic functions are simply sines and cosines. So the graph of this thing's position versus time would be a sine and cosine wave, and so we call it harmonic motion, because in math, harmonic means sines and cosine functions, okay? All right, so we had a mass on a spring. It was bouncing up and down, and in lab, the second part of lab, you guys asked, how does the period depend on the total mass? And I think most of you figured out that if you plot the square root of the total mass versus the period, you got a pretty straight line. The intercept was pretty close to 0. And so we can conclude that the period of the system is proportional to the square root of the mass. Now, this is different from the pendulum. For the pendulum, we found that the period does not depend on the mass. But for this system, it definitely depends on the mass, and the period is proportional to the square root of the mass. So if we were to do some other experiments, we could probably tease out the rest of this, but here's the short story. For a simple harmonic oscillator, a mass on a spring, the time it takes, the period, the time it takes to complete its cycle is equal to 2 pi times the square root of m over k. And that should look familiar. It's very similar to the equation for a pendulum, but a little bit different. In the numerator, we have the mass now. The mass matters. In the denominator, we have the spring constant, and they are both inside of a square root, which means if I make the mass 4 times bigger, the square root of 4 is 2, the period would only get 2 times bigger. Okay? So just remember that the mass is going to have to be in kilograms. That's what this is telling you here. The spring constant has to be in newtons per meter, and then you can calculate the period using this equation. And of course, if you ever need the frequency, that's 1 over the period, but we've already covered that in the last lesson. All right, so here's an example. A bungee cord is an example of a harmonic oscillator. It is a system that acts just like a spring, so springs don't have to be metal. Things that are elastic act like springs. And so if I have a 50-kilogram person attached to the bungee cord, and the bungee cord has a spring constant of 65 newtons per meter, then what is the period of oscillation? Well, the mass and the spring constant are known. They're in the correct units. And so I can simply evaluate this expression to find the period. I plug it all in, and it takes 5.5 seconds for this person to go up, 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 and then down, 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 down. So they are going to oscillate on the bungee cord just like your mass on a spring in lab, and the period is 5.5 seconds in this case. What would happen if I wanted to solve a slightly different problem? Suppose I want to know what is the spring constant. If I know the mass is 1 kilogram and I know the period is 1.7 seconds. So in this case, I have a mass on a spring. I know the mass and I know the period, and I'm trying to find the spring constant. So I'm going to try to solve this equation for K. Now K occurs or is found inside of a square root, and it's in a denominator. So we got to do a little bit of math to clean this up to be able to get K by itself. The first thing I would do is square both sides. Square everything on both sides. So T becomes T squared. 4 pi squared is what you get when you square 2 pi. And then M over K is inside of a radical, so it just gives, the radical goes away. I can now multiply both sides by K to clear the fraction, and I get this. And now remember, I'm trying to find K. I can divide both sides by T squared. So there's my algebraic solution, and I can plug in my numbers, and it turns out you need about 13.7 newtons per meter as the stiffness of the spring in order to produce a period of 1.7 seconds with a 1 kilogram mass. Okay? So this is going to form the basis of what we study next. Musical instruments, anything that has a string that vibrates is a simple harmonic oscillator, and we'll talk about all those connections. But right now, you're going to solve a problem set involving these ideas with this equation. So that's your job for today. Okay? All right, good luck.